your exam will have 6 problems, and it'll be broken down this way. So problem number 1, you're going to have a list of differential equations. You're supposed to identify them, classify them, and see if there's any way to solve for them. But you're not going to solve for them. Okay? So the hardest step, I think, in a lot of these problems that you would get would be looking at a problem and deciding what section was this in. and if you think about that, then you get to think, oh, okay, if it's in section 2.3, then that means I must be using exact equations or whatever 2.3 was. And so you want to be able to identify a differential equation by how they look like so that you can identify which method of solution you're going to take. Number 2, I'm going to give you a differential equation and a general solution. So I'm going to ask you to, 1, to verify to make sure that that general solution satisfies the differential equation. So essentially the check your work part that we never do, but you're supposed to do. So putting your solution back into the original problem to see if it works out. And then I'm going to give you an initial condition, and then you're going to try to solve for the arbitrary constants using the initial condition. So those are some of the problems that you guys might have seen in your homework set. So it should be manageable. This is the modeling part. This is the 1.3 part that I initially had. So I had a problem written down, but like I said, it's still going to be a modeling, which is an application problem, and you're going to, instead of coming up with the equation, I'll give you the equation and the differential equation, and then you just need to solve for it. Now, when you solve for it, I'll ask you to interpret your results based on the problem. So if the results were, if this is a question about something falling from the air, and then you solve for that differential equation, then you're going to try to explain the components of what you got, and then answer the question like, what's the terminal velocity, or how long did it take for this to hit the ground, or whatever question that I might ask. Solve for initial value problems. So for this one, I'm going to give you 2 initial value problems, or maybe 1 initial value problem and 1, I forgot. But I think this one is going to be similar to your last quiz, which is doing a first order linear with an initial value and then an exact equation. So there's going to be 2 problems here. I don't know if they're both going to be IVPs. Maybe I need to change this. And then the other one, you're going to just find general solutions, and you're going to use, I think we had 3 or 4 substitution methods that we went over in section 2.5 or 2.6 or something like that. So you're going to try to use some of those methods. And then the last problem will be Euler's method. This is where a calculator would be handy, where I'm going to give you a differential equation. So it's a first order differential equation. And then I'm going to give you an initial condition. And then I'm going to have you do probably no more than 5 steps. So I'm going to give you an H and then a terminal X value that would take no more than 5 steps for you to get to. So you're essentially going to be making a numerical table of values, and then you're going to give me the results in the end. Okay? And I'm not sure if this is something that you can test by finding the actual differential equation and then comparing your answer, or if it's something that we won't have a way to solve for the differential equation. But in any case, it'll just be an exercise on Euler's method. So you're not going to have the luxury of clicking and dragging Excel cells and stuff, but you can write a program on your calculator if you want. You can't use your computer. You have to use your calculator. Yeah. You can't use your phones either. I wish I could.
I get you bring in like some kind of signal jammer.
Is that legal?
Probably not. Probably not.
No, I don't have a signal jammer.
Educational signal jammer.
Educational. It's used for educational purposes only. So, I have a very, very rough copy of a review here. And the review is multiple choice, but I think it would just be good exercise for you to not, I mean, the idea here is not to get the answer, but to not to guess on the multiple choice answers, but to actually try to get, understand the solutions. And
You got that on Canvas?
it is now in Canvas as of like about 20 minutes ago.
What area am I looking for?
So we're at the home page, and under class lectures, there's an outline and notes, and then the next set is review.
Is there an answer key for the review?
Yeah, no. Wait.
Wait, what? On this side.
Oh yeah, look at that.
Oh, hell, that's the answer.
So Adam, there is an answer key. But like I said, the answer key just tells you the correct answer out of a multiple choice question, and I think based on my outline, you probably want to study this review sheet a little bit differently from just trying to figure out A, B, C, D, or E, right? Some of these are third order differential equations, which clearly is not going to be on the test that you're going to have to try to solve. But in these first few problems, they're just asking what kind of differential equation they are. And then once you get past that, then you have, this is kind of like a word problem. So I think this kind of mimics some of the problems that will be on the test, but then to try to get the feel for the actual test, then you probably want to go a little bit deeper into some of these things. Like for this one, for example, and this is a first order, it's nonlinear, but it's a first order differential equation, which should be something that you should be able to solve. So whenever you see something here that looks like you might be able to solve, then I suggest that you try to solve it, even though it doesn't have any values here or any solutions. So like this one, this looks like it's either a linear, homogeneous, separable, exact, or Bernoulli. So once you figure out what it is, then maybe you should try to solve it as well. Okay, so solving for that, I won't have the solutions, but you guys work together as groups, I'm sure you guys can figure it out. Okay? All right, so what do you suggest we do? We can try to jump around and try to solve for random differential equations here, or go in order from the top down, or go home. And any ideas? What?
How do we jump around ones that you recommend?
Ones that I recommend. Yeah, I guess so.
We practice a Bernoulli one.
A Bernoulli? Okay, let's see if there's a Bernoulli one. What's Bernoulli? What's a Bernoulli?
Oh.
What's a Bernoulli equation?
dy dx plus dxy equals some function of x times y to dn, or some power.
Okay.
That was the d equals y to the 1 minus n substitution.
Like maybe this one?
Yeah, that looks like one.
All right. let's do that. So here you have a list of solutions. Now, if you're doing a multiple choice test, which you're not, you could just take these answers and put them back into the original equation, kind of like check your answers, see which one's the correct one. But since that's not what this is, let's actually try to do this. Oops, I don't have my thing set up. All right, so for the notes today, I'm not going to rewrite the outline. You can just get the outline from Canvas. Let's see if we can solve for this. If we can identify this as a Bernoulli equation, y prime is equal, or y prime, and just for the sake of making it look like the pattern, maybe just rewrite some of these things if you need to. So n is equal to 2 in this case, right? And what we want to do is we want to make a substitution. Did we use u or something? 1 minus n. So that's 1 over y, or y to the negative 1. And what we want to do is we want to multiply this whole thing by this, right? Of course, we also have to change with any substitution, this is a substitution method, we have to change the y prime with the dy dx into du dx, since we're changing everything into u's. So let's figure out what that's going to be. Du dx is going to be the derivative. We subtract 1, right? So minus 1 over y squared dy. If we solve for dy dx, because we're going to replace that, we get this negative y squared. It's a negative, and the y squared goes on top. But then that's not what this is. We have to change this back into u. So what's u equal to? Or how does this become a u? Any ideas? Y is equal to u to the negative 1. Is that right? Negative 1, multiply the powers. So this becomes u to the negative 2. Wait, you guys helping me out here?
I don't know, what is this method?
This is the Bernoulli, and for Bernoulli we need to substitute u equals y to the 1 minus n.
That's the method,
This is
y,
what
1 minus n.
y to the 1 minus n, yeah.
Okay, 1 minus n method.
I guess. It's a Bernoulli equation, and it's a substitution. So I don't know if we call it a Bernoulli method or what. Yeah. I don't know. This is my relationship between u and y,
So
and
you put both.
is that right? That's right, right?
I think so.
Yeah.
I was just wondering.
In my head, I took both of them to the -1 power. But if we look at it as a fraction, yeah, and then you do the reciprocal, and you'll get the same thing. Thank you. dy dx. So I think if we make that last substitution where y is equal to u to the -1, then this is negative u to the -2. And that's what I can replace my y prime with. Okay, is this okay? I'm always afraid to move on because I probably did something wrong. I'm glad I'm not taking the test. All right, so let's do the substitution. So we have minus u to the -2 du dx minus 1 over x. Now y was u to the -1, and then y squared. I think we figured out y squared was u to the -2. So now I have a differential equation that's all in u. And if I clean this up a little bit, like divide everything by u to the -2, or I guess we can think about multiplying everything by u squared. I guess negative just to make this really clean. This would just be du dx. Minus minus is a positive 1 over x. U is equal to -1. And now it's the whole point behind the Bernoulli substitution is to rewrite your differential equation so that it's a first order linear differential equation. And we do have, in fact, a first order linear differential equation. So now that you have this, you integrating factor. You do some integrating factor business. So this is your p function with respect to our integrating factor. And this method has you figure out this mu function that you're going to multiply everything by. And this is equal to the antiderivative of 1 over x. I think it became positive. So it's okay. Yeah. I was just checking up to see if there's any errors that I might have done even before that with a negative sign. It looks okay. So this is an ln function on the power of e, which is just going to give us x. And remember, I don't know if anybody ever worked out that the plus c here kind of just merges with the plus c at the second integral that you do. So we don't consider the plus c here. And so we multiply everything by that. And so we have x du dx plus 1 times u is equal to -x. You have to remember to multiply the right-hand side by the integrating factor as well. And what happens is that this left-hand side is a product rule. And we're going to take the antiderivative of that. So antiderivative of the derivative of a product, x times u of x. And u is a function of x, so that's why it's dy dx, whereas x is a function of x, it's just the derivative is just 1. And so we're going to integrate negative x dx. All right, so this is just x times u equals negative 1/2 x squared. And let's throw in a plus c right now. And then u is negative 1/2 times x plus c over x.
So if we would have had a plus c on our u of x, it would have been x plus c.
It would have been, well, I think the plus c would be up here as a power, which would make it a coefficient of x, like an a. It would be up here, right? Plus c. And then that would be e to the c. And then that would kind of merge into the rest of the stuff. All right, unfortunately we're not done because this is a function of x. This is u is a function of x, but our original problem was in terms of y, so we need to do some more work. And remember that u is equal to y to the negative 1 power. So let's make that one more substitution. Let's call this x over 2 plus c over x. And then if you want to solve for y, you just take the reciprocal. Oh, you know, the reciprocal. And common denominators will make it look a little bit neater. In fact, if you're going to try to compare the answer, none of the answers, oh, no, B looks like that one. I was going to say none of the answers would look like that because if I was writing solutions for this, I'd combine common denominators and write it as a simpler fraction. Let's see. 2 over 2, x over x. So this would be 1 over 2c minus x squared over 2x. So y is going to equal to 2x over 2c minus x squared. I guess a 2c can also be a new c if you want. So I think the solution in the practice test is this 1 over this thing or 1 over this thing. Okay? Yes?
I just have one question on the top. When it was negative 1 over y dy dx, how do you get the negative y squared?
Oh, this is, yeah, this is 1 over y squared. I took the derivative. So its derivative is negative 1 y to the negative 2. So it's negative 1 y to the negative 2 is the y squared in the bottom. And
But why is dy dx?
oh, I solved for dy dx. And then I multiplied both sides by y squared. And so that cancels this by negative y squared. So this actually was brought to the other side. And now this is du, the coefficient of du has a y squared. Wait, I'm writing all over this. It's making it look messy. So this is what I have right here. I want to solve for y prime or dy dx. So I would multiply both sides by negative y squared, negative y squared.
Okay.
I switched this on you. So this is the dy dx. I put the dy dx on the
Other side.
left side now. And then I put this whole thing is on the right side.
Okay.
Yeah, I did a little switch on you. Anything else? Does it look cool? Does it look manageable? It's like a two-step process. The Bernoulli gets you to the first order linear, and then you do the integrating factor. Yeah. So this is the tricky part is here. You have to be, here you're playing with power, and with great power comes great responsibility. Only in a class like this would that work, right? So you have to be careful with negative exponents and switching things over to the other side and stuff like that. And so this is negative 1 power, so just imagine if it was negative 3 or something like that. You have to be really careful with how you approach that. I think the first time we did this, if you look at the notes, with the first time we did this, we had y to the 4th or something, or 1 minus 4. So that got really tricky, especially when you're trying to do some back substitutions. But you should expect to get a first order linear in U. And if you don't get this, then there's something that you might have done that was incorrect in your solving for dy dx, and in your solving for y and solving for u. So be careful. If you don't get a first order linear, then you did something wrong. Okay? Yeah.
How do you know what to multiply with? How do you know
Multiply by this?
Right, yeah.
Oh, because I want the du dx by itself.
Okay, so whatever makes it.
Yeah. So I mean, technically, you would divide by this. You divide by
Yeah.
u to the negative 2, but dividing by u to the negative 2 is like multiplying by u to the positive 2.
Yeah.
And so that's a style preference. I did it this way. If you're okay with dividing negative exponents, the key is playing around with negative exponents. If you're good with that, then you can think about this as a big division. Yeah, well, we didn't really get it alone, but we want it in this form where the du dx has no coefficient. And so by getting rid of that coefficient, then we're kind of just looking at this p of x over here.
So it doesn't matter what it does to the other parts, it just matters if you get rid of the coefficient.
Well, that part matters, but then you definitely have to have a u here and no u's here. So it has to be in the form of a first order linear. If you have a u squared somewhere, or if you have a 1 over u somewhere, then you did something wrong up here. Alan? Oh yeah, you guys get a sheet of notes. Sorry, I forgot to tell you. You get a sheet of notes back and front to bring to the test. So you can put whatever you want there. You can put, a table of integrals. You can put some examples of these things. You can put a picture of your mom. You can write a poem for yourself to get you motivated, or a prayer, whatever works. But you can have some examples and stuff. 8.5 by 11. So, as you're doing this, to try to look at the process, try to write down examples so that you'll come to the test, you'll be comfortable. I'm not asking you to memorize anything, so you should know how these things are.
I wonder how many questions there will be on this.
Well, you'll have 6 questions, but, multiple parts. So like the first question, you'll have 4 or 5 of them. And there's a lot because all you're doing is you're identifying these things, classifying, identifying. This one, again, 2 or 3 parts. It's just dealing with one differential equation, and then you do things to the solution. This one is just one big problem, but it'll, again, revolving around this one problem, we'll have solve for the general solution and maybe solve for a particular value, something, or a particular solution. Solve for the IVP. This one you'll get 2. So the first part will be integrating factors. The second part would be exact equations. So you'll get 2 for this. For number 4, you'll get 2 problems to do. For number 5, this is the substitution. You'll get 2 problems also. 2, 3, 2. 2 problems. Maybe 3. I'm not sure. Well, this is Bernoulli's. This is we did a couple of substitutions, right? We did a Bernoulli. There's like 3 or 4 substitution methods in this section. Bernoulli's just one of them. The other one. Exact. Yeah. So there might be something that's not exact where you have to make it exact, so you do a substitution. What's the other one? Alan, what did you say?
There was the like y equals bx or x equals b1.
Yeah. So I think that, which one was that? Is that the homogeneous? Yeah, the homogeneous differential equation. And there's another weird one where it's like if you have a ax plus by plus c, you have a function of that, then you could do that substitution as well.
What section is it?
2.5. 2.5. So questions, 2 to 3 questions from section 2.5, and then Euler's method is just one question, and that one question you'll have to create a table and make multiple things. Maybe I should have written that down. All right, what did I say? I forgot what I said. What did I say? 7? 4 to 5. This is one question with multiple parts. 3 parts. Yeah, so the general solution, check your general solution, and then particular solution, there's an initial condition involved. Modeling is just one question. Solve for the IVP. The first one is going to be the first order linear integrating factor. And then part B is exact. And then find a general solution to the DE. This is 2 to 3 questions. What section was that again? You said, Victor? 2.5. And then Euler's method. Well, Euler's method. Okay. Oh, here. Is there, I don't know if there's an Euler's method here. I know it is. But I spent a whole lecture on it, so I feel like I have to. In the past, I did, I just kind of glossed over it and stuff. But here I spent time, so I feel like I have to commit to doing. Is this a good one? Number 2. It has to be first order for us to be able to work it out. Let's do number 2 in Euler. Oh, we need initial condition, yeah. What should our initial condition? 0 usually. Y of 0. Where's y of 0? This is where I get in trouble. I start making up the problem without. Let's say y of 0 sine 0. Let's go y of 0 is equal to 1. I don't know where that's going to take us. And let's go to y of 2. That's what we're looking for. And then we'll say h equals 0.5. So you need these pieces of information to be able to do, with our limited resources on an exam, you need these pieces of information to be able to do Euler's method. So what we want to do is we want to write the slope, the derivative by itself. So we'll have sine x minus 3y. And this is your f of xy function. So we're going to need x and y's. X of 0, I guess I think I had it set up like this. X of 0 is equal to 0. X of 1 is equal to 0.5 steps. We're taking steps of 0.5. X of 2 is equal to 1. X of 3 is equal to 1.5. And then x of 4 is equal to 2. And that's where we want to end here. And the only y we know is the first one. And for us to get the other y's, we need to use the function and its derivatives. So, let's see. Our formula is y sub n plus 1 is equal to y sub n plus the slope, which is y prime. And then this is a slope that's evaluated at the previous point. Times, do we have to multiply times x? Oh, h. Might have to multiply by something. I forgot what. Okay. So, good thing you guys have a sheet of notes, right? What? Ooh. You didn't. You want one? Yeah. No. Okay. So, what if I do a homework in that section and not count it for your grade? Okay. All right. Oh, geez. Now I have to. Is somebody going to email me this? I forget.
You listen to these recordings, I can just shout it. Put a 2.6 homework on, but don't make it graded.
No, I don't. I don't listen to these recordings. I take it home, I render the video, and then I upload, and that's all I do. I don't ever know what I said.
Put them on YouTube. I like to think that someone would like sit down and start following our classes. It's like
Actually, some people have followed. I don't know if they followed my class, but I used to have honor students that do special problems in Calc 3, and there's one who apparently made a mistake, and I didn't catch it. And so there was somebody that was watching the videos that complained. There's an error here. So what? All right, so here's where a calculator will come in handy because we have to try to find the sign of 1 or something. Oh no, just sign of 0. For this one at least. So it'll be sine of 0, because that's x sub 0, that's the previous x value, minus 3h, and h happens to, or 3y, sorry, 3y sub 0, which is 1. So this is 3 divided by 0.5 plus 1. Is that right? 1 plus 1 minus 6 times 3 times 1.5. I thought you. I'm getting some reciprocal stuff all mixed up. Okay, so this is 1/2. Negative. Okay. Wow. So that's y sub 1. Ish. Well, this is exact. Yeah. The next ones won't. All right, so we got y sub 2 is negative. Oh, this went negative. I wonder if that's good. By good, I mean correct. I wonder if it's correct. So this is my new y plus h. Unfortunate that y and h are the same, but I try to make my h look different from my y. Sine of, now I have a sine of 0.5. Oh, another 0.5. This is my x. Minus 3 times negative 0.5. Okay, there's a lot of 0.5s here, but you know that these 0.5s are all different, right? So this 0.5 is y sub 1 plus this 0.5 is h. This 0.5 is x sub 1. And this 0.5 was y sub 1 again, per our formula. All right, so now you definitely want to use a calculator. Sine of 0.5 in radians, please. I hope it's negative, because this is going to keep going, popping back and forth, positive and negative, then something's wrong. Anybody got something? Let's have 2 people work it out. Oh, there's 2 people working it out. Everybody else is just waiting. Positive? Oh, no. What is it? Maybe this wasn't a good problem to do. I'm worried that if things are going positive and negative, there might be some issue.
And the one comes out to be a wobbly thing, so it seems like it should be.
Maybe. Oh yeah, there's a sign in here. All right. Well.
That's what the solution looks like, so it should be wobbly.
We can't solve for this, by the way, right? This is a first order linear, so integrating factor business. You can try to solve for this if you want. All right. So the next one, if we want to continue, 0.4897. So that's your y. That's your previous y now. You're looking at y2. 0.5 is your h. Sine of 1. 1 is the previous x value minus 3 times y. Now you get another. So this is what Alan was complaining about. It is tedious, and I'd prefer that you guys work this out using technology. But
1.175.9.
the next one?
So 1.5 paired with 0.1759. How many decimals?
Ooh, sounds like you got yourself a program, huh?
The old one works. The old one works. And then the last one, T is
Yeah.
Yeah. I was wondering if we have to bring a calculator. Because I don't have.
I guess I'm gonna have to buy one now.
I'll loan you a calculator. How many people need a calculator? Don't have a calculator with them? Okay, so I'll bring a TI-83 or 84 for you guys. So you just have to be able to plug in, like, be able to compute like sine of 3 or some weird stuff like that, which we can't do by hand. All right. Brian gave us the answer, so I think we'll be good with this. Well, I'm done. I don't want to do any more.
So what is it? I can't even see it. It looks like it goes up the screen.
Oh.
Minus 0.5, 0.489,
0.1759. 1759.
that would be y of 1.5.
Yeah. More importantly, it's this last one. So if you check your solution, if you put 2 into the function, I hope you're getting close to like 0.4, 0.41.
0.32.
Oh.
And it didn't go negative at any point between 0 and 2. It doesn't go negative until like 3.46 or something. Then it starts to like oscillate up and down across the x-axis.
We did this right?
It looks like it.
Yeah. Let's see if there's any Euler method.
I mean, yeah, I just plugged the differential equation into a solver and got a function for it, and then changed the constant so that at 0 it was 1.
Yeah, watch the Big Bang Theory.
Yeah.
They have they came up with an app. All you have to do is take a picture of a differential equation, and then they solve it. Did you see that episode?
Is that, did they really make it?
No.
Try that?
No, doesn't really
I'll pay
exist.
for that app.
Let's see. This is sine x minus 3y. 0, y is 1, x n. Partitions 10. Geez, I just want 2. 5. I want 5 partitions. Well, let's do 50 and see what happens. 0.31. Is that what you got closer to 0.32, right?
Yeah, that's pretty damn close.
Yeah. So our solution was not very good.
Like, I mean, I can understand that we didn't do as many things, so it wouldn't be as close, but like, could you expect it to turn negative even if the function never did?
I might, because that, if it's something really steep and it goes down, then it would take it to.
Yeah, I mean, at 0, this thing is like, if you want to look at it, it's kind of funky. It starts out looking like this exponential falling down.
Oh
to 0,
yeah,
and then
see.
it turns into like a trig thing.
Okay, let me sketch it. All right, so the issue here. Did I ever show you guys how it works graphically? So I think the big issue here is that we're starting off at this point, and the slope at this point is very steep negative. So what happens here is that we're taking steps of 1/2. And so with this really steep slope, it kind of brings us down here first. And then so bringing us down here will make it really tough for us to recover back. I think that was the big issue in this particular problem. And so going back, your slopes would be positive now, but your actual curve, according to what Alan found, kind of looks like this. So this steepness over here brought you a little too far down, and by the time you're down here, you're trying to get back up. And then you're going to start missing quite a bit because of that first step. So the better thing to do is to, of course, to cut this up into smaller pieces so that your smaller piece wouldn't go down so much. And so that's just the nature of using a numerical method with big steps instead of small steps like you're supposed to. So like this one, the smallest step they have is 10. Was it 10 before? Oh, we tried it with 50. So the smallest step that they have was 10, and this thing never seemed to have gotten negative because our first step was too big of a step. All right. So hopefully your problem won't go too weird like this. Okay. Do we have any more that you guys want to do? Let's see. What do we should probably look at the outline. Anything else that you're interested in covering? Exact? Yeah. Wait, let me see if he has something easier.
The substitution with the
AX plus B? Yeah. I think that's easier. With the exact equation, if something's not exact, you have to multiply that by some n, x over n stuff. So that's too hard, so you guys can figure that out. Let me see if I can find a problem with the substitution with the ax plus by plus c. Oh, this one. All right, we'll have 4x plus 2y plus 3 quantity squared is equal to y prime. Let's let that be our differential equation. So this is your right-hand side function. It's not linear because the y is being squared, and it's not separable because we can't split this up, and it's not a Bernoulli. It's not an exact equation, is it? No, I don't think it would be. So anyways, this would be a case where we have to imagine that this is an ax plus by plus c scenario. And then if we just let u equal to that, 4x plus 2y plus 3, and then we're going to change our differential equation again into solving for u instead of solving for y. We'll go du dx. Du dx is equal to 4 plus 2y, or 2 dy dx. Plus 0, that's gone. So this is our dy dx. And then I think I want to solve for this, dy dx. I think I had an issue solving for this one time. I want du dx minus 4 and divide that by 2. Let's see. 1/2 du dx minus 2. I don't know if that's easier. Any case, we'll do the substitution back. We'll replace this dy dx with this whole 1/2 du dx minus 2 is equal to, all the u's are gone, all the y's are gone, I mean, and now you just have a function of u. It's separable, is it? 1/2 du dx is equal to u squared plus 2, and then I'll multiply everything by 2. Du dx is equal to 2 times this. And then now it's separable. Du over u squared plus 2 is equal to 2 dx. Yeah, this is some arctangent thing. Arctangent root 2 or something. Arctangent u over root 2 or root 2 times u. Good thing you guys have a sheet of notes, right? Pull out an integral formula and say, hey, this is the arctan. So this is the antiderivative of this is the arctan of u divided by, you have to take a look at 2 as if it was something squared, so that's square root of 2 squared. And then integrate the other side, that's 2x plus c, that's where you get your constant. And then solve for u, tangent and square root of 2. And then change it back, to that. 4x plus 2y plus 3 equals that thing that we have. And I think you could solve for y here if you carry on. And let me just check the solutions, the possible answers, that is. Oh, shrunk. Something with a hey, look, the last one. Except they have 2 root 2. What happened?
Yeah, because we make a u substitution with u. Sorry, it's called a v substitution. Divide both sides by 2.
Here?
No, multiply both sides by 2. We should divide the denominator by 2.
Are you talking about here in this step?
Yeah.
So you, oh, I want this to be 1. I think I got you. Well, there's some integral thing here. Table of integrals. So with some table of integral magic, there's an extra root 2 that popped out somewhere. Yeah, something happened. So you just figure that out, and, and you're good to go. And your answer is going to be this last one. Okay? Yeah, good thing you guys get a sheet of notes. All right, so next time we'll just come in, take the test. If you're done, then you can leave. And good luck studying. One sheet of notes, calculators, anything else? Okay, see you guys next time.